All right, so I wanted to show one more example here. This is from a group of Lukin at Harvard. Recently published in Nature Physics. They call this a quantum convolutional neural network. Okay, so what do they have in mind? Well, it's also a quantum circuit, similar to this, but with some twists. So let's see, can represent this. So first you have a number of qubits, and each pair of them, each adjacent pair, you do some 2-qubit operation, and then you do the same on the other nearest neighbors. And so on. Then you take this output and you measure on half of the qubits. So you do a measurement here, a measurement here, measurement here, and then I do a single qubit operation with D, on that qubit that was not measured, and then this single qubit operation is conditioned on the measurement result. Then you continue with the unmeasured qubits, and you do again 2-qubit unitaries, and so on. So then you do measurement on half of the qubits, single qubit operation, conditional measurement on the remaining ones. And then in the end here, you have a number of qubits, you do some unitary on all of them, some sort of fully connected operation. And then you measure on one of them to get some output result. For example, a label, like in the previous example. So how is this then a convolutional neural network? Well, can anyone tell me what the classical convolutional neural network is? Well, it's a feed-forward neural network like the one we saw back on Tuesday. It's often used for image recognition. It has parts first where it sort of scans a filter over a whole, so it's not fully connected, but it just looks at one part of the input, like a few pixels of an image. And so only the input from there is fed to one neuron, and that does some operation. And then you do the same thing with the next cluster of pixels from the input, you feed it to the next neuron, and you use the same weight. So it's just like here, they are using the same unitary operation here, everywhere in the first one. And then you sort of pool this information from these filters. You do some final processing with some fully connected layers, and you get some output. So it's similar to what they're doing here. They're sort of using these measurements to reduce the number of qubits that are carrying the information. And then finally they process it with some unitary that can connect all the qubits, or you do swap gates or something like here, so all the qubits interact. So. Now, what's interesting here is these measurements. So these measurements are, for one, used to do this narrowing of the network, coarse graining of an image, for example, that you're looking at. But then they are using these measurement results to influence what action is done, or operation is done on the remaining qubits. And this introduces some nonlinearity, because this measurement is a nonlinear process. And then you condition on that, you effectively have managed to introduce some nonlinearity in this circuit. So that's the basic idea. So the measurements introduce nonlinearity. And then again, they do training by gradient descent. But again, there is no back propagation anywhere. And I don't see how it would be possible to implement. So again, I think there is a problem with slow training, basically here. And I don't know if you can sort of offset that by being much better at processing certain data. But it's unclear to me. People are proposing these architectures, but it's sort of unclear if they have actually give some advantages. And there seem to be some disadvantages. If there's no big advantage, then this lack of back propagation, I think, makes just the training slower than what the classical neural network would. So these examples were very recent, and there are not so many works exploring this yet. There is another type of neural networks where people have looked more at quantization. And that's the last topic I wanted to discuss. Let's erase this. Does anyone know what a Boltzmann machine is? Or have you heard this? Have you heard this term, Boltzmann machine? Yes. So, a Boltzmann machine is a number of neurons that are connected. Usually, you have some neurons that are called visible. Some are called hidden. So this column is visible, this is hidden in this case. Then you can have different connectivity between these layers. So if you just have connections that go from the visible layer to the hidden layer and back. So in this case there are no connections within the visible layer, there are no connections within the hidden layer. This is called a restricted Boltzmann machine. Then you can have a fully connected which, as the name suggests, is you have connections between all neurons. You can also have a deep, and then a deep Boltzmann machine is just more hidden layers. Yes.
Yes. So how is this different from?
Yes. So far, I have not explained how this is different from the feed-forward neural networks. Now, in the feed-forward neural networks that we looked at, you have some certain input that's in some layer, and then you feed that to the next layer, and to process it, and you feed it on. Here, the connection is two ways. And let me explain. So you have some energy functions. Now I will do this for the restricted case. So, okay, one thing I should say here is that these V, the visible units, and the H, the hidden units, they are what's called binary neurons. So they will take the value 0 or 1, or minus 1 and plus 1, depending on how you do that.
Continuous domain or discrete? Is it either?
It's one, yeah, it's either or, it's discrete.
Okay.
Just these two values. A, it should be V, of course. So these two terms are just some energy functions for each individual unit. These you can call them biases. And here, this W is what's called a weight matrix. So it says something about the strength of each connection here. Now, this energy function helps to, or is what gives a probability distribution for the values of these neurons. So the probability of being in state V and H, or V and H are vectors of the states of these neurons, is given by 1 over Z, where Z is some partition function, times e to the power minus this energy function. So now we can maybe understand why they are called Boltzmann machine, because this is a Boltzmann distribution. So this factor is just some normalization. So what we have here is some probability distribution for the states of the neurons, and this probability distribution is set by this energy function. So it's set by these weights. So by training these weights and biases, you can realize new probability distributions. And what you usually do is that you have some data. You can sample from some probability distribution, and you want your Boltzmann machine to mimic this probability distribution, so that you train the weights, and then you have your Boltzmann machine there, and if you sample from it, you are sampling from that probability distribution that you got your data from. Yes?
How many years do we need to approximate and can
Any kind of distribution, I don't know. So yeah, I don't know if there are theorems for that.
Is there only one layer of visible units, or do you have an output layer?
So here what you're actually training on is sort of the probability distribution for the visible units. So I'm going to write it down. So you have some data, you train on some data, which is some probability distribution over V. So you don't know what or you're averaging over all the states in the hidden unit. Now, you do this, again, the training is you're minimizing some cost function. So the cost function should tell you how close your the probability distribution of your Boltzmann machine is to the probability distribution of your data. Usually you use this cost function. And you train using gradient descent in some form. And it's usually good if you can somehow efficiently sample from this probability distribution. People have thought about using quantum algorithms for this, sampling from some probability distribution, but it's unclear. Okay, so there is now some quantum versions of this. So quantum Boltzmann machine is, for example, discussed in a PRX from last year. What you basically do when you make this quantum somehow is to replace those binary neurons by quantum spins, qubits. And then this energy function that you have is then Hamiltonian for a system. And again, there's sort of, yes, people have looked at quantum versions of this, but it's sort of unclear how good it is. So one idea people have is that maybe if you have now qubits instead of these binary neurons, then you can represent some particular probability distributions better. Just in particular probability distributions that arise from quantum physics. So, and perhaps represent some distributions. But, so in this paper at least, still they don't know how well this scales with the sizes. They don't know how, if the performance actually is better. So, and they say when they train this again, they encounter some problems that it seems a little more tricky to train these than to train classical Boltzmann machines. One interesting thing about these quantum Boltzmann machines is that you can perhaps use quantum annealers like D-wave machines to implement these quantum Boltzmann machines. Then one can also note that actually these restricted Boltzmann machines, these classical ones, are actually turning out to be pretty good at simulating quantum systems. So there is this whole, in sort of the area where you use classical machine learning to tackle quantum physics. This is one hot topic, so to use restricted Boltzmann machine to represent quantum states in a sort of efficient way. Alright, so you can see that for the quantum versions of neural networks, well, there are ideas how you can make something quantum that looks like neural networks in various ways. It's still very unclear if you can train these networks or these quantum networks well. It's also unclear if they are useful for anything. Actually, it's the impression that I have at least. So there's a lack of sort of rigorous results of actual proof that this is better and it's better by this much. So this is sort of different from the problems that we discussed yesterday with these support vector machines and so on. There you have more these clearly defined quantum algorithms. You're applying them to some linear algebra problems. You can calculate like exactly what is the scaling with the size of the problem, and you can make clear comparisons with the classical algorithms. here it's harder. Maybe this is because there is a lack of rigorous results for classical machine learning also. Like, we don't know how well they scale, or like what hyperparameters to be used in training for to get good results even for classical neural networks. So maybe it's no surprise that it's hard to be quantitative about this quantum network. So it might be a matter of like we need to wait for the larger quantum computers so we can try and see. That's my impression so far. Any questions? Comments?
I was wondering, why do we call that hidden layers? Maybe because the direction of that.
There's no like, so it's hidden because in the end when you're looking at this probability distribution for the data, and when you're sampling from probability distribution, you're sampling for the visible neurons. These hidden units, you don't look at them, but they are there to help construct the probability distribution.
It feels like the connection is starting from the visible units to the hidden units, and then from the hidden units to the visible units.
Well, there's no direction to these connections. So the connections is just sort of in this weight matrix. And it's just to represent this energy function. It's encoded here in this weight matrix. So it's different from the feed-forward neural networks that I was sort of drawing on Tuesday, where you have a specified input, and then you're feeding that information to the next layer, which somehow processes it, gives an output that's fed to the next layer. So it's a different thing. Here you're generating some probability distribution that you can sample from. You're training your network to mimic the probability distribution that you drew your data from. Okay, anything else? Well, in that case, that's the end of this course in Advanced Quantum Algorithms. Thank you all for being with us. Also, once watching from home. And I wish you all a Merry Christmas and Happy New Year, and good luck on the home exam, which you will receive in January.